Okay, just a minute. Let me check if the session has started or not. All right. Hi everyone. So this is Utkarsh Gupta, and today I'm going to do this video editorial for the third hardest problem, substring probability from the CodeChef March Long Challenge 2021 Division 1. Okay. So I think this problem was only in Division 1 or maybe in Division 2 also. But yeah, so this is the third most hardest problem. And the problem statement is quite simplistic, but the solution is not that simple. It's not very hard as well. It's not a single very difficult problem. It's like a mixture of a lot of sub problems, and you need to know the things about all of them. Right? The problem statement is kind of simplistic, so let's read it first. So you are given two strings P and Q. So consider some uniformly randomly independently chosen non-empty prefix x and non-empty suffix y of the string, right? So you have the string P, you choose a prefix and you choose a suffix uniformly, randomly, and independently. Okay. And the string z is formed by concatenating x and y in this order, right? So first you put x, then you put y, and in that way the string z is formed, and you want to find the probability that z is a substring of q. So q is the string. So basically what you want to do is you want to take a prefix of the string p, you want to take a suffix of string p, you want to combine them, like concatenate them in that order, and then you want to check if that string is present as a substring in the string q or not. Okay, so that's what you want to do, and you want the probability of that thing, and it can be shown that the answer. So yeah, this is just modular arithmetic. Okay, so let's see what exactly do you have to do here. So in this, you will have a string, something like let's say A, B, C, D, E, F. Okay, and then you will have another string, right? So let's not consider the other string for now. Okay, so let's say this is the string P that was given to us in the input, right? And what we can do is we can pick a prefix of this thing. Let's say I pick this prefix and call it X. Okay, and then I can pick a suffix. Let's say I pick this suffix and I call it Y. Okay, so then Z would be the concatenation of both of these, so it will be like A, B, D, E, F, right? And X and Y can be overlapping as well, so this is also valid. Like you could have something like this can be A, B, C, D, and this can be C, D, E, F. X and Y can be like this. So then the yellow Z would look something like this: A, B, C, A, B, C, D, and after putting A, B, C, D, you're putting C, D, E, F again. Right? So something like this. The only restriction is that both X and Y have to be non-empty, right? So they cannot be empty. Okay, so yeah, you have to make sure of that thing. Something like this. Okay, so we want to find the probability that this thing exists, and first of all, we have to see how many values this Z can take. Okay, so Z cannot take a lot of values. It is just n square exactly. Like if this length is n, if the length is equal to n, then the total number of values that this Z can take are equal to n square. And let's see why. Because the total number of values that X can take are n, basically the number of prefixes, and the total number of values that Y can take are also n, the number of suffixes. And so for each X and for each Y, there's a Z, a unique Z. So in that way, you have n square total ways of forming Z. Okay, right. So these many ways are there to form a Z, and for all of these, if you can count how many how many of these occur in the string Q, then you can easily find the probability. The probability would just be number of substrings found. So the number of substrings found divided by n square, right? So this is the number of substrings out of the n square that are found in Q divided by n square, right? So something like this you can do. This approach, like if you try to do it naively, it would be very slow. You can maybe do it in I think cubic or biquadratic time. You can do it using some optimizations. You can make it cubic, otherwise just by brute force you can do it in biquadratic time, right? So but this solution would definitely not work for any subtask. You can see that the cubic time complexity won't work even for PQ smaller or equal to 2000, right? So even in this subtask, that thing won't work, right? So we have to come up with some kind of with a lot of optimizations actually. But first, let's see what the cubic solution would look like, or even the biquadratic solution. So let's see what the solution would look like, right? So the easiest solution would be something like, if I have the string A, B, C, D, I can make all possible Z, right? So I can make a Z like A, D, then I have A, C, D, then I have A, B, C, D, and A, B, C, D, right? Then a lot of other ways again, something like A, B, D, A, B, C, D, A, B, B, C, D, then A, B, A, B, C, D. So in total, like I won't write all of them, but in total there will be 16 such strings, right? So you can form all of them, and then you can try to find all of these strings in your string queue. Okay, so find all of them in queue. Right, and then what you can do is you can just count how many of them were actually found in queue, and that's it. That's you're done, and it will be depending upon how you implement it, it will be around cubic or biquadratic time, right? So yeah, this is very slow, but at least we are able to solve it. Okay, so now let's try to come up with some optimization. It won't improve the time complexity much, but yeah, it would look like a more cleaner solution, right? So let's try that one. Okay, so we can see that in all of these strings that we formed, there's a certain partition that divides it into the prefix and the suffix part, right? So maybe we should use this thing and make our solution a little better by using this fact that we can divide them like this in two parts. Okay. Okay. Wait a second. Am I audible? Hello. This fact. Okay. Okay. Cool. So yeah, so you can make like instead of finding all of these strings in queue, what you can do is you can just find all the prefixes in queue, and then you can find all the suffixes in queue, and you want them to be adjacent to each other, and then you can say that they're forming a big thing, right? So let me show you this to you by an example. So let's say if we had q equals the string q is equal to something like a x r p x a b x c d, something like this, right? So if we had something like this, and p is again a b c d, right? So what we can notice is we find the prefix a here, we find the prefix ab here, and we find the suffix cd here, and so on, right? So we can find these type of things. And let's say if we had another a here, then we have a prefix a, and we also have a suffix cd here, right? What we can do is we can merge these two, and that way we get a ACD, right? So and all of these things just depend on the length. So this is the prefix of length 1, this is the prefix of length, suffix of length 2. Okay, so this is the 1 prefix, this is the 2 suffix, right? So in this way we want to form pairs, like adjacent pairs. It would look like something like this. um, let's say you have something like peak, okay, peak you are taken, let's say UV, right? So U is a prefix, prefix of length U, and then you have a suffix of length, suffix of length V, prefix of length Q, like this. Okay. So once you have this thing, what you can do is you can consider this thing as a pair, and you want the number of unique pairs, right? So number of unique pairs. And now a few people might think that now it's very easy because you cannot have more than, okay, so you would think, by the way, I'm already telling that it's wrong. So the next thing that okay, I'm gonna make it on a new page, and I'm gonna write it's wrong already. Nobody gets the idea. Okay, it's wrong, but I'm gonna tell what a few people might be thinking. So these type of pairs, these are only formed when you have something, when you have two things adjacent, right? So this has to be adjacent to this, and then only it can be formed, right? So you would think that number of pairs won't be, number of pairs can't exceed length of Q. Okay, and let's see why one would think that, because we have a string Q, and only at adjacent positions, like from here we need a prefix. Let's take this example, like at this point we need a prefix, and at this point we need a suffix, and we're taking both of them and we're merging them, and that's how we're getting a prefix and a suffix, and that's how we're making a pair. So obviously it seems like the number of pairs cannot exceed the length of Q, right? But as I said earlier as well, that this is wrong. So let's see why is it wrong. So let's see the example, why is it wrong. It's a simple example actually, right? So let's say P equals A B B B B, something like this, okay? And then Q equals A B B B, right? Something like this, okay? So what will happen is, at this point you will have a prefix of length 3, and at this point you will have a suffix of length 3, like the suffix of length 3 and this prefix of length 3, right? And anywhere else you don't have both a suffix and a prefix, right? So only at this point you have this thing, and you're thinking that you have only one pair, 3 comma 3. Okay, let me make sure my camera isn't blocking this thing. Okay, cool. So you think that you only have 3 comma 3, but that's not true, because I agree that this is a prefix of length 3, but this is also a prefix of length 2, and this is also a prefix of length 1, and similarly this is a suffix of length 3, but you also have a suffix of length 2 here and a suffix of length 1 here. So basically this is not the only pair, you have more pairs. You have like 1 comma 1, you have 1 comma 2, you have 2 comma 1, and also 1 comma 3 and 3 comma 1, and all such pairs, right? So you have all such pairs, so you get the idea, right? So there are a lot of pairs, and obviously the total number of pairs can be around n square, and that's a lot. Like there are a lot of pairs. The solution is still hello comodices. Okay, so yeah, so there can be a lot of pairs, and yeah, we cannot handle all of them, and the solution will still be cubic even if you do all this, right? But still, this is worth looking into. Like, we'll probably figure something out. Uh, okay, so we'll probably figure something out. But let's see how we can actually do this thing. How we can mark that here we have a prefix of length 3, and here we have a prefix of length suffix of length 3, right? So for that we use the prefix function. Okay, for that we can use the prefix function. You guys might have heard about it in the KMP algorithm. Let me know in the comments if you want me to teach this thing, how it works, in the live chat or in the comments afterwards. You can let me know. But yeah, so this is available in CP algorithms, the prefix function. It basically stores the length of the longest prefix suffix, right? So I'll tell you what that means. It's something like, let's say if you have a string A, B, A, C, A, B, A, B, A, C, something like this. Okay, so let's say you have a string like this. So what we want is at each index, we want the longest proper suffix prefix. Okay, so let's see what a suffix prefix is. So at this index, basically what we want is, we want the longest length such that the prefix of that length and the suffix of that length are the same, right? So like these are all the prefixes and these are all the suffixes. So we want the length of the prefix and the length of the suffix to be same. So let's say here we can see that the length will be 1, because if we take a prefix of length 1 and if we take a suffix of length 1, they are equal, right? So at this index we have 1, at this index we have 0, because like if we have a suffix of length 1 and a prefix of length 1, they won't be same. Then at this point we have 1, here we have 0. Okay, so something like this. So you have to put the length of the longest prefix suffix at all points. Like here it is 2, because we can see that this AB is the same as this AB in the same substring or the whole string. So LPS is like, I can show you from this example here. There must be some example here, right? So you can see that this is a string. Sorry. Yeah, so this is a string from S0 till Si, and the LPS is K here if this K is equal to this K. Like these K characters are equal to these K characters. So only in this substring, like if I'm talking about this substring, okay, so we want the longest prefix to be equal to the longest suffix. Like we want the longest length such that the prefix and suffix are the same. So like this AB is equal to this AB, something like this, right? So that's why we have a 2 here. Then here I think we will have a 3, because you can see that this ABA is the same as this ABA, right? Okay. Then at this point, I think we again have 2, because this thing is the same as this thing, but you cannot go longer than that. Okay. Then at this point, you again have 3, I think, because this thing is the same as this thing. And at this point, you have a 4, because this thing is the same as this thing. Okay. So if you use this algorithm that is given here on this page, I can even teach it if you're interested. You can find this entire thing in just linear time, right? So this final algorithm, it takes like it uses some observations. You can see that there are 2 observations here. It uses both of them to finally get a linear solution, right? So you can do it in linear time, in just one time, right? So this is the code for that. Using this, you can get all of this in just linear time, right? So something like this we're interested in, right? So let's see why we're interested in this thing. So again, let's take that example when P was equal to ABCD. Okay, and let's say Q is something, anything. Okay, so Q can be something like, I don't know, again we will take the same example. Let's say AX, ABX. Okay, and then ACX, ABCX, something like this. Okay, so let's say the string is like this. So what we will do is we will make another string. We will make a string R. R will be equal to P plus some symbol that is not supposed to be in P or P and Q both. So let's put the dollar symbol here and put Q. So it will look something like ABCD dollar. Then we have AX, ABX, AC, X, ABX, something like this. Okay, so let's say we have this thing. And now if we form the prefix function of this, at this point we will just have 0, 0, 0, 0, everything is 0, right? On the dollar sign also we have the 0, but on the right side, basically this is the string q, right? So what will happen here is we will at this point we will always get the length of the longest prefix ending at this point of the string p. So something like here we will get 1, here we get 0, then 1, then 2, 0, 1, 0, 0, 1, 2, 0, something like this. Okay, so you can see that if we are getting a 2 here, then that means that this is the same as the prefix of length 2 from the starting. And you can see that we want exactly something like this. So at this slide I explained that we want a certain prefix and we want a certain suffix, and we want to make a pair of both of these things, and we want to keep all the pairs. So we will see what we will do with those pairs later, but yeah, but we want those pairs. Okay, so yeah, using KMP algorithm we can kind of find at least the prefix, and now we want the suffix as well. So for getting the suffix, what we can do is we can reverse both P and Q. Okay, so we can reverse both of them. So this will become like DCBA, right? And if we reverse this thing, it will become like yeah, this is the reverse of this. Okay, so we can reverse this. Okay, and when we perform the same algorithm in the reverse direction, what we can do is we can similarly get the suffixes, right? So it's kind of easy to understand that if we do everything in the reverse direction, we will get the suffixes. Okay, so similarly, like this is the length of the prefix ending at a certain point. Like we know that if we have a 2 here, it means that this thing coincides with the prefix of length 2. If we have a 2 here, that means that this thing coincides with the prefix of length 2. So all of this can be done in linear time. Okay, and then if I use the same thing on the reverse strings, then in just linear time I can get all of this for suffixes as well. Okay, so let's say we have already done this. Let's say we are already at this step. Okay, so let's see what this step would look like. So for the prefixes, we would have something like 1, 0, 0, 0, 0, 1, 2, 0, 1, 0, 0, something like this. Okay. Okay, so we are finding prefixes and suffixes of P which are substrings of Q. Kind of, and we're finding the positions at which that's happening. Okay, so we're just taking the longest one, something like that. Okay, and so this thing we did for the prefix, and then if we reverse the strings and do the same thing, kind of like if we do that, then we can do the same thing for the suffixes as well. So it would look something like this is 1, this is 2, then this is 0, 0, 0. I think everything else is 0. Okay. Yeah, so using the prefix function, we are able to get something like this, right? Okay. Now, how do we use this? Because as I said on this page that this thing is wrong, that you cannot take all the pairs and put them in a set and then just count them. And it's wrong because if the string is like this, so let's just take this example actually. This example is actually very good. And let's take this one. So this example would look something like, let's say P equals a lot of A's and then a lot of B's, right? So let me write the Q then. Let's say Q is equal to a few A's and a few B's, right? So first of all, we're going to write it for the prefixes. So for the prefixes, it is 1, 2, 3 and 0, 0, 0, right? Then for the suffixes, it is 1, 2, 3 and 0, 0, 0, right? So you can see that we can form a pair of 3, 3. We do have a pair of 3, 3, but this is problematic because this pair of 3, 3 is the same as a pair of 2, 3 also. So you can see this is the 2, 3 pair also, this thing and this thing. Then it is also a pair of 1, 1, this thing and this thing. Okay, so yeah, that's problematic. And what's actually happening is so this 3 can also work as a 2. So how do we know this information beforehand that this 3 will work as a 2? So you can, I can show you another example that I mean obviously it depends on the string P. So let's say if P was equal to something like AB, AB, right? So AB, AB, A, right? Or something like this. So it will be like 1, sorry, if you write the prefix function, this will be 0, 0, 1, 2 and 3, right? So this is a 3 because this is the same as this. This is a 2 because this is the same as this, and this is a 1 because this is the same as this, right? And now the thing is, AB can only work as a 2 or 0, right? So this AB, it can work as a 2, but after the 2 it can only work as a 0. But the 3, which is ABA, it can also work as a 1. Okay, so you can see that this ABA is a prefix of the string, I agree, but this A is also a prefix of the string, right? So that means there is some type of relationship between these length of prefixes, this array. There are some relations. So you can see that this 3, if you go to this 3, this is joined to 1. So basically 3 is joined to 1, then 2 is joined to 0, and 1 is joined to 0, right? So you kind of have a tree like structure. So if I make 0, 1, 3, 2 like this, so it is something like 3 is joined to 1, 1 is joined to 0, and 2 is also joined to 0, like this. So you have a tree like this. Because a prefix of like if you have this 3 is joined to like this 3 is joined to 1, something like this. Okay, also the 5 is joined to 3. So if I write just the indices 0, 1, 2, 3, 4, 5, so this 4 actually this should be the length 1, 2, 3, 4, 5. Okay, so we know that this 5 is joined to 3 and 4 is joined to 2, and so something like that. So we can form an entire tree like this. 5 is joined to 3, 4 is joined to 2. Yes, we're just joining this index to this LPS. Okay, so 5 is joined to 3, 4 is joined to 2, then 3 is joined to 1, and both 2 and 1 are joined to 0, right? Something like this. So this will always form a tree because like we're always joining towards the left side, and everything will end up at 0 at the end. So obviously this will be form a tree. And let's see how this tree will help us. Okay, so okay, so let's say if we have a tree like this. So if we have a tree like this, so what will happen is like this is, let's say, the from the prefix part. So let's say if we have a pair of 4, 3, and I'm talking about this type of pair, right? So if we have a actually more like this type of pair, that we have a prefix of length u and a suffix of length v, right? So if we have a pair of 4, 3, this pair will also work as a pair of 2, 3, which will then be 0, 3, but we don't count this one. Okay, so we can just ignore this. So 4, 3 will also work as 2, 3. Similarly, your 5, 3, 5, anything, 5, y, let's say 5, v will also work as 3, v, which will also work as 1, v. Let's again see this thing in this example. Okay, so if we form the prefix function here, it is just 0, 1, 2, 3, 4, 0, 0, 0, 0, 0, 0. Okay, so and if we write the indices, these are 1, 2, 3, 4, 5. Okay, so here the tree is just a line, something like 0, 1, 2, 3, 4, 5. So we have the links like this: 5 is joined to 4, 4 is joined to 3, 3 is joined to 2, 2 is joined to 1, and 1 is joined to 0. Okay, so we can see clearly from this thing that a pair of 3, 3 will also work as a pair of 2, 3, and it will also work as a pair of 1, 3. Okay, just based on this tree, because 3 is joined to 2, 2 is joined to 1, and 1 is joined to 0. So that's why this thing will happen. But we don't only have a tree on the prefix part, we have a similar tree on the suffix part as well. Okay, so you can see that even in the suffix part we have a similar tree, which is why 2 comma 3 will also work as 2 comma 2, and 2 comma 2 will also work as 2 comma 1, and so on, right? So you have a lot of pairs. You have two trees like this, and let's just form both of the trees. So till now it wasn't very tough, just a collection of a lot of different concepts, and you want to bring them together. So let me just quickly revise what I just did. Okay, so first of all, we use the prefix function. Okay, we take the string p, we take the string q, we make a string r, that is p plus dollar plus q. We form the prefix function like this, and using this prefix function we actually make an entire tree. Okay, so the tree would look like this. The tree is actually formed over just the string p. It would look something like this, or maybe like this, depending upon the string. So we form the prefix function of the string p, and then we have the index and the LPS, one based index actually. Let's say the length and the LPS, and we're joining the length to the LPS like this. So we get a tree. Okay, so we use this tree, and using this tree, we want to do something. Okay, so just how we had this tree for the prefix, as I said in the beginning, that instead of doing this thing only for the prefix, we will reverse the both the strings, and then we will have something like p reverse. Then we will also have the q reverse. So we will find make a string r dash, which is equal to just a second. Yeah, PR plus dollar plus QR, something like this. And then we will form the prefix function again, and then we'll form another tree. Okay, so the problem has reduced a lot. It has become something like we have two trees. Okay, so one tree would look something like this. Okay, so one tree would look like this. So this can be the prefix part. Okay, then we also have a tree on the suffix part. The suffix part tree would look something like this. I don't know, maybe 4, 3, 2, 1, something like this. Okay, so let's say the 3 goes to 2, 4 goes to 1, then both of these goes to 0, something like this. Okay, yeah, so we can have the tree for the prefix, and we can have the tree for the suffix. Okay, something like this. So let's say we have both of these trees, then let's see what the pairs would mean. As I said earlier, that we have pairs like these, prefix of length u and the suffix of length v. What this pair would look like is an edge from this tree to this tree. So I'm going to use red to mark those. Let's say I have a pair 2, 4. So this pair would look something like this. We have an edge from this 2 till this 4, right? And this automatically means that we will also have an edge from this 1 to this 4, and we will automatically have an edge from this 2 till this 1, and from this 1 till this 1, and so on. So you will have all of those edges, and you have to see, and you have to count the total number of edges, right? So yeah, so the problem has reduced to this part, and here's where the real problem starts. Okay, so now you can just forget about everything else, forget that there were strings, forget that anything was happening. Now you have to just focus on this part, that you have two trees, and you can easily get all these pairs, right? So you can make some of the pairs. Let's say you have one pair 4, 3, and let's say you have another pair that is 1, 2. Okay, right? And then what you want to do is you want to kind of count all of the total edges that will be formed, because these edges will end up making more edges. So like 4, 3 will automatically make a 4, 2 as well. Then this thing will also make 2, 3, and also a 1, 3, and a 2, 2, and a lot of edges, right? So we have to count all of these edges, and yeah, so that's what we want to do. So let's see how we can do this. How we can do that. So let's try to simplify this problem a little bit, because this is actually a very tough problem and we cannot solve it in just one go. I mean, some people can, but yeah, it's a little difficult to understand. Okay, so as I said, from these two trees we have edges like this. Let's say one edge is like this, let's say the other edge is like this. Okay, something like this. And the problem here is, in both of these trees, this edge means that there is this edge as well, and there is this edge as well, right? So that is what's making this problem tougher, because we have a lot of edges and we have to keep count of how many edges are there, and we don't want to count the duplicates, right? So yeah, we'll see what we can do about it a little bit later. But for now, let's say what we let's try to see what we would do if this thing wasn't happening in both of the trees. Um, like right now we have this thing that this edge also causes this edge, and also causes this edge, and also causes this edge and this edge, right? But if this wasn't happening, then it's simple. You just have to count all of these edges. So that is very, very simple. You can do it. Now let's make it a little tougher, that this thing will happen in only one of the trees. How would you solve it now? Okay, so it's something like, let's say if you have this edge, this would automatically mean that you will have this edge as well, but this won't mean that you would have this edge. Okay, so let's just assume it for a little bit so that we can come up with a solution, and we will try to improve that solution to make it work for the other part as well. Okay, so a new problem, a new easier problem. Okay, so first let's try to solve this, and let's try to use the experience that we gain here in the original problem. Okay, so a new easier problem is something like, we have two trees. Okay, there can be a lot of branching. Two trees like this, and okay, what's happening is we have some edges from this tree to this tree. Can have a lot of edges. Okay, and an edge x comma y automatically implies that there will be another edge px comma y, right? So if this is the x, this is px, that is the parent of x. Okay, so x comma y, if that automatically implies px comma y, then what do we want to do? How will we calculate this thing? Okay, so then it's not that difficult. It's actually a bit easy. What we want to do is, we don't care about this tree at all. Okay, so we can just ignore this tree, and whenever we have an edge x comma y, we can just store y here. Like, let's say this is x, we can just put y here. We can say that, okay, we have a y here, right? Let me just label this, like this is 1 2 3 4 5 6 7 8 9, and let's say this is 1 2 3 4 5 6 7 8 9, something like this. Okay, and now if we have an edge like 7 comma 2, okay, instead of representing this as an edge like this, we can just ignore the structure of this entire tree. We can ignore that this tree exists, and we can just say that this 7 has a certain set in which a 2 is present. Okay, and that's how we can handle all of the edges. So like we had 7 comma 2, let's say if we had 5 comma 6, then again we can do the same thing. We can say that this 5 has a certain set in which a 6 is present, and yeah, something like this. So if we had 4 comma 6 as well, we could say that this 4 also has a set in which 6 is present. And let's say if we had 4 comma, okay, did my camera just stop working? Just a second. Okay, let's leave it. It's not working. So, okay. Mm, just a second. Okay, this is bad. Yeah, let's leave it. Okay. Right. So if we had something like 4 comma 3 as well. So in this set we can have a 6 and 3 both. Okay. So um, instead of just going like uh, as I said, this if we have a 6 here, we will have a 6 here as well, and we will have a 6 here as well, and so on, right? So basically what we want to do is we want to take for each vertex the total number of distinct elements that are present in the sets of all the like the entire subtree. Okay, so for this entire subtree we want the total number of distinct elements that are present. So we know that if we merge these two sets we will get only 6 comma 3, right? And that way we will have the total number of distinct elements. Okay, so this is a simple kind of thing. On code forces there is a problem there called Lomsad Galrel, which is almost this thing only. Okay, so to solve such a problem we use the technique that is called small to large merging. Okay, so basically at each vertex we keep a set, and when we are merging the sets we make sure that we're merging the smaller set to the larger set. Okay, so let's say we want to merge the set B into set A. What we will do is we'll pass both sets by reference, and if the size of set A is smaller than the size of set B, what we will do is we will swap both sets and then we will put all of the elements of set B into the set A. Okay, and the reason why we're doing this is because uh, we don't want the time complexity to increase a lot. Okay, so like obviously if you're inserting the bigger set into a smaller set, you're transferring a lot of elements. Okay, so that can make it n square log n, right? But if you use small to large merging, which is also called DSU on trees, this works in just O of log square n, n log square n. Okay, let me give you some resource about it. It is also called SAC, by the way. So there is a blog on Code Forces about this thing, right? SAC DSU on tree. So this was written by ARPA, right? So yeah, so this works in n log square n. You basically keep a set at all of the vertices, and then you merge those sets. And you make sure that whenever you're merging two sets, you're merging the smaller set into the bigger set. Okay, and this works in log square n. Okay, so there's no explanation here, so I'll explain why this works in log square n. So y is SAC O of n log square n. Okay, so yeah, it's kind of easy. When we merge from small to large, what happens is the size of the set gets at least double. Okay, so size is becoming at least double. Right, and this is the thing that we're going to take advantage of because the size is getting at least double, it means that we cannot keep on doing this thing for more than log n times, because then the size of the set will be too big. It will be bigger than n. Okay, so this thing can be done only log n times. So what this means is, a single element, you will have to insert a single element not more than log n times. So what will happen is, um, if you have a lot of sets, and if you insert one element from one set to another set, it takes log n time, right? But since you're doing this only log n times, for each element it is log square n, so it is log square n for each element, and since there are n elements, it becomes n log square n in total. Okay, cool. So yeah, in this way we can do it. We can solve the easier problem. Okay, so that solves the easier problem. So that solves the easier problem. Using SAC. Okay, so using SAC we can solve the easier problem, and yeah, so that will be solved like this. But now let's come back to the original problem. Okay, so we can do this thing, but the original problem is actually a bit tougher than this. So in the original problem there are actually two things happening simultaneously. That if we have edge x comma y, it implies that there will be a edge px comma y, and it also implies that there will be an edge x comma py. So since we have both of these edges, uh, it's really clumsy, because now you see, it's not just that you have all of these edges, you have all of these edges as well, right? So that makes it really complex, and we have to figure out something to do it. Okay, so till now we had used SAC, and but now we have to do something even better, and let's see how we can try to do that. Okay, just a minute. Okay, I have no clue why this isn't working. Yeah, let's leave it. Oh, I think it started working. Just a second. I have no idea why this is happening. Okay, sorry about that. Okay, right. So what's happening is, um, right. So from for this edge we have all of these edges as well. So we have to make sure that that works, right? And for that, what we can do is we can kind of use a few other tricks. Okay, so now we need a lot of other tricks, and let me list them. So we need to know about LCA. We need to know about the Euler tool. That is also called flattening of tree. Okay, so we need to know about LCA. We need to know about the Euler tool. Okay, yeah. So we need to know these things to be able to solve the like this part. Okay, and in this, the observation is kind of simple. It is something like, let's say if we have a tree like this. Okay, and for one vertex of the other tree, if we have these edges, okay, so it will automatically mean that we have, like, if we have an edge with this and if we have an edge with this, it will automatically mean that we have all of these edges as well. Okay, what we can do is, when we take this vertex, like when we make this edge, instead of counting just one, we can count the depth of this thing. Okay, so we can just count 4 at once. And for this, if we count 3, that will be a problem because we're counting all of this twice, right? So what we can do is, the entire set that we already have, let's say we have already taken these two elements, right? So if we have taken these two elements, that means we have taken all of these vertices, right? And now if we take this vertex, or let's make it a little better. Now if we take this vertex, we need these two vertex also. Okay, so we need the LCA of this element with some element of the tree such that it is the lowest point. Okay, so this will be the LCA, like the LCA of this and this is this. That means this vertex has been already taken, but this hasn't been taken, so we have to add this to our answer, right? So something like this we have to do. So for this, we need to be able to solve a certain problem, and that problem is, if you have a certain set, right? Let's say if you have a set in which there are a lot of elements, you want, for a new element, you want to find the lowest of its vertex. You want to find the lowest of its in fact the highest of its ancestor that hasn't already been taken, right? So we know that all of these have been taken, we know all of these have been taken, all of these have been taken. So for this, we need the highest ancestor that hasn't already been taken. Okay, so there might be a lot of ways to do this. One of them is to use LCA. You can see that if we find the LCA of this with this, we get this, and we know that this thing hasn't been this thing has been taken already, so this hasn't been taken. Okay, so one thing that you can do here is you can use binary lifting here. Okay, so you can use binary lifting to kind of binary search on the highest ancestor that hasn't been taken yet. Okay, but how do you make sure that the ancestors, whether a certain ancestor of this has been taken or not? So that will work out on the basis of whether there is any vertex in this subtree which is present in the set or not. Okay, so for that, what you can do is, you have the entire like when you do the Euler tool, you have the in out time. Okay, so at this vertex you have the in time and the out time. Okay, what you want to do is, you want to find at least one vertex in this entire thing that is present in this in out time. Okay, so let's say if there is a vertex in this subtree. Okay, so if it is in the subtree, it will definitely be within this range, this in out range. Okay, so you want to find at least one vertex in this in out time, and that way you can do this. Okay, so for that, you just have to you can perform the binary lifting that will work in login time, and then you can do this, like find at least one vertex that is in this range, this in out range. Okay, so that is also simple. You can just use the lower bound in the set, something like this. So you have to keep the vertices in the set ordered according to the Euler tool. Okay, and there's also one other way without binary lifting. It uses some technique. The technique is just that if you have a lot of vertices, okay, that are already present in the set, and if you add a new vertex, okay, so the vertex that we require, like we require this vertex, right? So this will either be the LCA with the nearest with the vertex with nearest in time on the left, or the nearest in time on the right. Okay, so let's say the in time of this vertex. So let's write the in times actually. It will be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, something like this. Okay, so if you want to find this vertex, what you want to do is you want the closest vertex. Okay, so let's say this and this are taken, right? So we will either, and this is also taken. Okay, so we will either take the LCA with 7 and 8, or we will take LCA with 8 and 10. Okay, and the lower one of those will work. Okay, so here the lower one of those, like with 8 and 10 we get the LCA this, so this is definitely higher, and with 7 and 8 we get the LCA this, and this will work. Okay, so you want on the both sides the nearest in time, and you want to find the LCA with them. That way you will get that vertex, and you can add the depth like that. Okay, so now I'm going to show the code. I don't have my own code, but I'll show the author's setter's code actually, because he uses the same idea I read his editorial, and he uses the same idea. Like his idea is very similar, just a little bit different in the way he formed the edges. Okay, so that's why I'm going to show this. Okay, so if you read this thing, like it's a bit complex to understand, complicated to understand. So that's what I explained in my video. But yeah, okay. Let me show the code. Let me actually copy this on my Sublime so I can explain it a little more clearly, like a little more easily, because this is actually very small. Okay, right. So to solve them, he first took the string P and string Q. Then he took the strings reverse P and reverse Q. Then reverse both of them. Then he has N and M. And right, so this is these are just the two graphs that he has basically to form the adjacency list of the trees. And he's making the tree for the forward direction and the reverse direction. Okay. Uh, in fact, I can call it the prefix one, and this is like the suffix one. Okay. Yeah, simply that thing. And you can see in the make tree function, yeah. Then the make tree function is just doing the KMP, right? So KMP is nothing but the prefix, like finding the prefix array. Okay. First you find the prefix array, and yeah, then based on that, making the edges of tree. Okay, so he's making the edges of tree like this, like with the length you are joining it to the length of the longest prefix. Okay, so yeah, that way you're storing the parent of each vertex, so you get the entire graph. And yeah, so he's just making the graph here. He'll make both of the trees like this. Okay, so he made the prefix tree and he also made the suffix tree. Now he wants to process both of the trees. Okay, so in both of the trees he's performing some different type of pre-processing, and let's see what he's actually doing. Okay, so for process T1 he's just doing this DFS T1, and yeah, okay, so I don't clearly understand what this is doing, but either way I'm probably sure process T2 is more important. Right, okay. Just a second. So in this DFS T2, which is a part of process T2, is doing everything that's required for the Euler tool in time basically. Okay, so he's storing the in time like this, and this is, I think, binary lifting. Okay, this is the pre-processing for binary lifting. Or LCA you can call it, right? So let me tell you a little bit about LCA as well. You can find that also on CP algorithms. Okay, lowest common ancestor using binary lifting. Yeah, that's what he's doing. Yes. right? So he's doing binary lifting using he's using LCA using this binary lifting approach. Basically, I'll also tell you what this actually means. So this is something like if you have a tree like this, then for each vertex you keep the first parent, you keep the 2 to power 1th parent, 2 to power 2th parent, 2 to power 4th parent, and so on, existed, right? Something like this. So based on that, it is easy to get the LCA. He probably even has the LCA function, right? So finding LCA using binary lifting, right? You see that the code is actually like the implementation for this problem is not very trivial. Like you have to do a lot of stuff, right? But anyway, right? So make both trees, pre-process both trees. Let me just see once again what pre-process T1 is doing. I think this is not very well commented, so I don't fully understand what this is. Maybe in my solution, this part is not required. The solution I explained, maybe this part is not required because I don't clearly understand why this person is doing this DFS. Something maximum. Okay, restoring the heavy child. So he's storing the heavy child actually for stack. Okay, so not required in my method. So it is not required in my method because in my method what I'm doing is I'm just merging smaller to larger regardless of what's happening. Okay, so this is another form of stack approach in which what we do is we take the biggest child of the tree. Okay, so like this is the biggest child. Okay, and we just copy the set of the biggest child upward and then we merge everything into that. Okay, so because we already know that uh, this set would be the largest. Okay, so something like that, and he's trying to pre-process to find which child should be the heavy child, and we call this the heavy child. Okay, but we don't really have to do it, and the reason why we don't have to do it is because let's say if we are merging this into this, then if we know that the size of this is smaller, so like if we know that the size of this is bigger, we can just swap both sets and continue. Okay, so yeah, so that's what I explained earlier. um, I had written a code earlier here. Just a minute. So it is something like to merge two sets. Just a second. Yeah, to merge two sets you can do something like you can take both sets. You can take both sets as the arguments, and then if the size of A is smaller than size of B, then you can swap them. Okay, this works in O1 time, by the way. Okay, and finally what you want to do is you want to merge B into A. Okay, this will always make sure that you're merging smaller to larger. Okay, so this is always merges smaller set to larger set, right? So you don't have to do this heavy child part. I'm not sure what this sub part is. Maybe that's something else, but probably you won't need that as well. Okay, so this is just some pre-processing like LCA and heavy child marking, etc. Pre-processing for LCA and marking heavy child like this. Okay, and okay, so and this part is just uh, this line just means answer equals answer divides by n square. Okay, that's fine. So all we have to do is we have to uh, find the answer, right? And for that he's doing this stack thing which he calls DFS heavy light. It is a bit like that actually. It is a little bit like DFS heavy light. Like it can be called DFS heavy light because you're finding the heavy child, you're leaving that, and something like that. So heavy is the child with the largest subtree. Okay, and yeah, so this is a bit complex, but just merging the sets. Okay, so this is a bit complex actually, but he's just merging the sets on the vertices, and he's keeping, like, along with the set, he's keeping the count of all the vertices that are taken from the other tree, and then while merging the sets, maybe he has a function for merging the sets. Maybe he's merging the sets here. Okay, right. So yeah, so that's what he's doing. He's finding the lower bound and getting the LCA like that. Okay, so basically you have to find the LCA, and using that you can get the highest vertex that has not been taken yet, and you can subtract the depth of all of them, and you can add that to the answer. Okay, so he actually has the current count that is global, I think. Yeah, so here is a global variable current count. You don't need that. You can maintain a value along with the set, which is storing the number of vertices that are taken from the other tree if you have the vertices of this set. Okay, so yeah, you can do that, and you can update it while updating this, like merging the sets. Um, yeah, so obviously this is very complex. The implementation is very complex. So the implementation is very complex. Okay, so yeah, obviously it is very complex, and you have to be really careful about everything, right? So you have to be really careful about everything if you want to do, if you actually want to do this. And there are multiple ways to do this. There are a lot of ways to do this. Okay, so I gave the general ideas. I mean, the general idea is. Let me write the general idea also. Okay. So the general idea is, first of all, use prefix function to make the prefix suffix pairs. Okay, and then make the tree of LPS, right? The longest prefix suffix, right? So you can also make the tree of that LPS thing, right? And using that tree, what you can do is, now what you want to do is you want to make the sack thing. Okay, do the sack thing, which is also called DSU on tree, and apparently heavy light DFS. Okay, something like that. And keep count of taken vertices and LCAs, etc. Right. So as I said, there are a lot of ways to do all this. One thing that can be different is instead of doing this binary lifting LCA, you can also do the sparse table LCA. Okay, and the sparse table LCA actually makes it a little like a little more intuitive, because you see you're finding like in a sparse table LCA you also use the Euler tool, like you use the Euler tool and the heights already. Okay, so you're already using the Euler tool and the heights in the sparse table LCA method. And what you want to do, high stoic being, okay, so you're already storing the Euler tool and the heights in the sparse table LCA method, and in this problem you only want the LCA and the heights and things like that, right? So it would make more sense to use the sparse table method instead of using the binary lifting method, because it is faster as well. It works in O1 per query, and when you're already in the log square end part, you want to you don't want to be wasting so much time in just finding LCA. So I think this binary lifting method would be better here. Okay, so yeah, I would say not here. I would say better to use sparse table LCA, or it is also called RMQ LCA, right? So I think the code is a bit clear now, but I would advise people to do it on your own. The general idea is just use the prefix function to make the pairs, then make the tree of the LPS, make the trees of LPS. There are actually two trees, one for the prefix, one for the suffix, and then you have to do the SAC thing. And while keeping the sets, you have to keep the count of taken vertices, and you want to get the LCAs and the heights quickly. LCAs, vertices, and LCAs and heights, etc. Okay, so you have to keep track of everything, right? So yeah, that's it, and that's it for today's session. Thank you for watching.